Hey everyone, so I just wanted to go over a quick run through of the installation of some of these OpenTD post-processing utilities and toolboxes that I have set up, and dive into some of the information that's output with you. So for one, if you scroll over to the products page here, this is the website, and you can come in here and view that if you want to. This will point you over to where you could download this, but the easiest way to get the download completed is if you open up Matlab directly. And I'm going to try to one-shot this without doing much video editing because I don't want to spend a ton of time on it. So I'm just going to walk you through live here, full installation and looking through some of the different outputs that are available. So if you come over into the Apps tab and then go into the Get More Apps, and we're going to come up here and search for OpenTD. I'm going to add this, and then open this folder, and then you'll see if you expand this folder some of the different items that are included with the download. There's a couple different readmes. I'd recommend checking into some of those for getting started. One of the first things we're going to do real quick too is just install this Matlab app, which I already have installed, but just same process. If you don't already have that installed, it'll just install in a similar manner there. And then we'll go into some of the utilities. So for one, I have included quite a few different examples. This example kind of script here is just meant to be a collection of different function calls that you can make and some different optional input arguments that these functions can handle. Just walking through some different use cases. I'm not going to go through this in detail, in this video, but definitely recommend reading through this and looking at some of the different options that are available for the calls. Again, just make sure you don't run this function because there's a whole bunch of different calls here. I would recommend you just copy, for example, this call to get save file data over into the sandbox, and that's what I have here by default. Just make sure that you're pointing towards a save file path that actually exists, and we can go ahead and run this real quick, but I kind of want to walk through most of the functionalities in the application and leave some of these different more programmatic calls and run-throughs to kind of the end user. You can read through here and really look at how you can set up your own calls to these different functions. So I'll run this for now. The first thing it's going to do is boot a parallel pool. There are some options in this function where if you don't want to have parallel processing used, you can turn that off. And that's included in some of these examples here. While this boots, I can show you, I guess. So like for example, this would be your input arg if you did want to use parallel processing. And all of these different functions I've released like everything here, so you can go ahead and open up this function directly even if you wanted to. Look at the different argument types that could be accepted to give you some more hints and some tips there. But the examples does call it out reasonably well. But if you're curious, in any one of these functions, you can go ahead and open it up and look into some more details here. So this finished running. Let's just wait and look at some of the outputs from the application itself, which is going to spit out the same thing, but we'll just kind of help walk through some different things at that time too. So it's going to go ahead and boot the application. The first thing that you're going to be prompted to do is to select a save file. So just going to browse for one of those real quick. And you'll have options on studying some subset or getting data for some subset of the save file if you want to do that. I'm just gonna, I guess I can cap this real quick just to make this video a little bit easier to watch. So comp times are reduced a little bit. We'll just do like the first 10 seconds at ballpark 1 second outputs. Looks like there's a steady state run here first two, or maybe just the beginning of transient and then thereafter. Don't entirely remember here. So for one, let's just go ahead and process using no custom references, and then I'll walk through what this does in a second. Okay, so I'm going to write this data to the workspace real quick. But before diving into kind of all these different structures and the information that you'll have available, I just want to show you what you can do with this information just in the GUI. So if I was interested in outputting some of this data to like some spreadsheets, then you can do that. So if I come in here and we're just going to dump this all on the desktop for now is fine. Every now and then that app will kind of disappear. You might have to click back into it. That's what I just had to do there. If you want to, you can specify some different file name. If not, it's going to use the save file name itself as a prepend. You can also specify some options here. So there's going to be a time-weighted kind of averaging and outputs done. And so if you wanted to do kind of some of that time-weighted post-processing over some subset of the data that you had processed, for like maybe the last 2 seconds or whatever that is, if you're doing like a cyclical run and you're outputting every timestamp throughout that entire run, then maybe you just want to do like the last set there. Kind of depends on what you're after, but you can process over some subset for the time-weighted data if you're interested. There will be a rate of change check to kind of check for stability to see if submodels have converged. So you can specify your units here and a value. Just delete the defaults. There will be an oscillation check. So like technically, your rate of change, you might not ever reach a true steady state, but it might be steady state in the nature that it's got some pretty normal kind of different fluctuation, like some sine wave type pattern kind of going on to it. And there's some different checks that go in and look for that kind of behavior. So you can go ahead and set your unit type and value for what that magnitude you want to check for is as well. So we'll go ahead and check both of these options as well. We're just going to export the raw data. I'll show you what that means, and we'll open them automatically. So these are getting spammed on another window right now, so I'll bring them over kind of one by one here. So for one, this is the raw data on the thermal side. So these are the different submodels, as well as, I'm sure those watching this video are familiar with Cinefluent. So, you're looking at some of the capacitances, and then if we scroll down far enough, we'll get into like heat rates and then temperatures. So this is just kind of all the raw data, right? And then along kind of each column here is at a particular timestamp. Okay, same idea here, but for some of the registers. So you can go in here, look at those. And then this is some of the fluid data. So there's a couple different fluid submodels in here. This is, going in. There's quite a few different data types, clearly, for a lump than a node. So this is just spitting out all those different ones as well. And then this is kind of the summary sheet. So this will output some different information about the save file itself, and just kind of like an overview. This time-weighted tab is, kind of specific to some of those inputs we were just walking through before for the rate of change and oscillation check and so on and so forth. You can go ahead and look through all these, yourself. It's going to do that time average study over the time period that you specified, and will tell you which times were included in that study here. So this is a more processed, I guess, organized selection of some of the information we were looking at for the thermal submodel, the raw data. In this case, we are looking at, for this thermal submodel, the capacity weighted average at this timestamp, for example, so on and so forth, but min, max, some other temperature statistics here. And then you can scroll along here to see all the different submodels that you might be interested in. So in this model, there's clearly quite a few of those. On the fluid side, it's a similar output, albeit maybe not as useful for fluid submodels, just because there's a wide range of kind of connections. It's not like you can really sub-organize these the way that you can with thermal submodels, but it was easy enough to include, so I went ahead and did that. Okay, close out of this, and we'll bring back up initial application. So that was, for one, I did write this data to the workspace before. We also just exported that and looked through all that. Next, we'll go ahead and look at what this plotting, built-in plotting function can do. It's relatively lightweight, but it mostly gets the job done. So if you're interested in some thermal or fluid submodels, so for example, if we want to see submodel 1 here, of course you can have multiple if you're interested in that kind of thing. You can look at some of the average temperature, capacity weighted, max, min, rate of change, so on and so forth. We'll just keep it at average. If you plot it below, then it's going to plot below. If you want it in a new window, it'll plot in a new window. Go over some register stuff here real quick. So if I go ahead and add a different register here, then I can plot that. Again, same idea, you can have multiple different registers. So pretty lightweight, but you can review some of the data in the save file easily here. If there were heaters in the submodel or in this model, then there would be some other items of interest specific to each one of those different heaters here. And these are the different data types that would be available for that heater. Okay, so let's move on to the visualize heat flows. So this is really probably one of the parts that was, for one, the most difficult, but for two, one of my biggest motivators of putting all this together. So what this is going to end up generating is a network diagram of all the different energy flows that exist within your model. So your first input is you have to select a time that you want to see these energy flows. So if we just select, for example, this output, that's fine. I'll leave it purely at defaults here so you can get an idea of kind of what we're dealing with, and then we can walk through some options here. So for one, this is a breakdown. We got 3 different plots going on here for total. This other plot is the linear, whether that be conductive or convective, and then radiative heat transfer breaks it down into kind of each portion here so you can better evaluate kind of what's going on. And it will draw a network diagram with line weights that are representative and weighted based on the amount of heat flow, so you can kind of easily see that. It includes the different entities for from and to, and the temperatures associated on average with that thermal submodel. So really some pretty interesting and useful information. I had a lot of fun building this and looking at all the different ways that you can visualize that. As a thermal analyst for quite a few years there, this is something that I always wished that I had. So hope that you guys enjoy that. So we'll walk over some different options here now. So we'll leave focus and exclude references, just set to none. We'll only look at total heat transfer, and we'll change up the layout to be force 3 instead. So really only one change, but now you can kind of get a 3D diagram just in case your 2D one's getting a little bit hard to visualize. With a bunch of different connections, this can help kind of view that information potentially a little bit easier. And again, it includes a timestamp and what we're plotting, here. So we'll set this back to auto, and now let's say that we are interested in, submodel 1 for whatever reason. And for 1, we'll leave this exclude references as is, and leave this as is. So for what this is going to do is anything that connects to submodel 1 will be displayed here. That also includes anything that connects, for example, you can see submodel 2 is connecting to submodel 1 but has interactions with submodel 3. If you were only interested in the immediate submodels that interacted with submodel 1, then you'd click nearest only. And so now this has been kind of filtered down, filtered down to only those intermediate or those immediate interactions. So like submodel 3 and some of these other ones have been pruned, and we're only looking at this. One other thing you can do, and I'll leave this up just as a reference. So this is the same output that we had for these inputs before. But if I wanted to, for whatever reason, just filter down the number of interactions that are shown, if you're just getting like an overwhelming number, if you have like a really interconnected model, then you can go ahead and change this value and break it down to only the most significant interactions. That's kind of how the decision is made about what's shown here. So if you were curious and wanted to only look at a few major contributors, you could do that kind of using this manner. One other thing, if you, for whatever reason, didn't care about one of your interactions and you just wanted to kind of eliminate that from consideration and look at the rest of these, so maybe, we didn't want to see these fluid submodel interactions with my thermal submodel, then we can come in here and say flow 1 and 2, do not want to see those. Those are now selected, and we will generate a new diagram, and the new diagram will no longer include those items, potentially making it a little bit easier to see. Again, you can increase this out to however many you want. Of course, at some point it will saturate if you have nearest only. If you turn that off, then it's going to draw up the rest of the map again. So pretty neat. Definitely recommend exploring some of the different capabilities here, and hope you guys find this useful. The trending tab here, this is how you look at kind of the energy flow, but not within the entire model. This is within some specific from to collection, but you can look at it over a transient time frame. So again, just using submodel 1 as an example, we'll look at the energy flow from submodel 1 to submodel 2, the total rate, these are the different options, and we'll plot this just along the side here. So as you can see, it's pretty steady, pretty much a constant amount of energy flow, and the negative sign is just showing that we're actually flowing from submodel 2 to submodel 1. So that's kind of what the sign difference is doing here. So this can be pretty useful, if you're interested in looking at how that energy flow is changing over the course of your run, or has some different orbital position, or whatever coinciding to your run. Okay. So that's a walkthrough of the different GUI options. I did mention that I would talk through these custom references, and let's go ahead and do that before we dive into these output structures, because it might be of use as part of that discussion. So not going to select any specific submodels here, which means it'll default to using all of them. And if we want to look at a couple different nodes, and you can tell there was a whole bunch of, this is a pretty node heavy submodel, so it took a little bit to generate this list. But if we look at, for example, these first 2 nodes, and we'll just throw these over here. You can do that. And then if I was interested in, for whatever reason, looking at some collection of nodes that spans multiple submodels, you can do that. All right, and if we wanted to look at some specific lump or a collection of lumps, we could do that. I'll just leave it at 1 for now. And if you were really interested, for more of an outside and edge use case, you can study a collection of nodes and lumps at the same time. So I'll walk through kind of more what that means in a second, but this might be of use, if you had some nodes and lumps interacting with one another and you wanted to see how those then were interacting with the rest of your system, you can kind of study those as a group. So the collection of nodes, you might want to use that if you've got a really large thermal submodel, but you're only interested in some specific nodes in that thermal submodel that you're most sensitive to or something. You could do that. Studying across multiple different submodels, again, I'm sure there's some use cases. Just, if you have things interacting again with the rest of the system, you can study that as a group. We'll go ahead and proceed with these selections and process this data. And I will add that typically if you're using some custom references that include different sets, it'll hit you a little bit harder in comp time, but shouldn't be terrible. Okay, so I'm going to write this data to the workspace for one. And I'll show you just real quick. We won't go over the export one again, but now that we have different collections, you can actually see those collections as well. So we're looking at the average temperature for this collection. If we wanted to, we can plot both of these, and note that this is a collection of both thermal and fluid submodels, which again, probably an edge case, but that is supported. Visualizing heat flows, it's going to be a similar idea. We'll go ahead, and if we were interested in these specific nodes collected together as one group, then we can see what those ones collectively, you know, kind of an overall sum of all the different interactions that are possible between that collection set and anything else. This will kind of show you what that looks like. Okay. Everything else, you know, pretty much the same idea. It's just wanted to get across the point that you can study collections of nodes, lumps, or a combination of both as well. So now let's dive into some of these output structures. And if you end up using this in more of a programmatic fashion, this might be of use to kind of see some of the information that's contained here. So for one, we'll go over the save file info. This is kind of just a lightweight call, and all this is going to do is grab information contained in the save file, but not actually pull that data. So it'll tell you the different times, you know, for example, that are in it, different names, so you can tell that we had a steady state before transient here. The different record numbers, which can be used to ping into grabbing specific timestamps or record numbers. Most of the functions accept either one of those as input arguments. If you're only interested in data at some particular time or within some time range or record number range. Thermal submodels, so like for example, I'll just throw this off to the side here. One sec. Okay, so I've got the thermal submodels here, that part of the structure, and what you're going to see here is just to break down all the different submodels, and that there's a one-to-one correspondence between the submodels and the node IDs. So for example, in submodel main, which is just, you know, kind of a default built into kind of TD, you will see that there are actually no nodes contained there, but it is a thermal submodel, versus like submodel 1 here at index 4 has a node in it, and it only has one node, and the number ID for that node is 1. You'll see bar has a bunch of different nodes, and this is all the different nodes contained within that submodel. Okay, so covers the thermal submodels and node IDs, fluid submodels and lump IDs. It's the same exact idea. I'll show you just briefly. You know, you got flow 1 is the name of this fluid submodel, and then in fluid submodel flow 1, there's only one lump, and that lump is numbered 1. Also contains the different registers in the model, just the names of them. The units, which you can look into. The path that was applied, the name of the case set or save file. Some different file attributes, if you're interested in that. When it was last modified, which can be really useful, is just like a timestamping of when you pulled information and the amount of runtime that this function took. Let's go into the save file data next. So this one's got quite a few different kind of outputs and branches. For one, you can look into the different inputs, just depending on what you supplied to the function will be shown here accordingly. And again, it's got a timestamp of when this data was pulled. Well, technically it's got a timestamp of when the save file was last modified. There's some additional telemetry on when this was ran. Let's go into the raw data here. So this is going to be, again, familiar for those of you that have used Syndifluent. We'll just dive into some of the thermal references here. So it's going to be a submodel. You know, this is capacitance of node 1, heat rate node 1 for the submodel, you know, so on and so forth, right? It's a big table of all of the raw data contained here. Fluid data, similar idea, just a whole bunch of different data types that might be of interest, you know, a bunch of different physical data types. So you can come in here and review those and grab that information if you want. I do just want to call out the get save file data function. You can optionally select only processing, for example, temperatures for lumps. You don't have to grab all the different data types here, so that's a capability that exists too. Register data is just going to give you a breakdown, time, record number, and the register name and value corresponding to that time. Post-process data is really pretty useful for the thermal side, fluid side as well to some extent. I'll walk over some of the nuances there. So on the thermal data, if we pop open the references, I'm just going to throw this off to the side real quick. Okay, so this is my references, and again you can see this is actually a list because we studied a collection of different nodes. So if we were interested in seeing some of the statistics for that collection of nodes, we would come, again, first index here in references, which is going to point us to the first index here. And this will be the data corresponding to that collection of references. And there's quite a few different columns, different statistics here. For a thermal submodel, again, this is a single node, so you could go ahead and look at that if you're curious as well. Okay, we'll leave it at that. For the thermal data, fluid data, kind of similar to what we were seeing there in the thermal data. Again, references in the same manner as what we had before, but this time we've only got a single one here because we did just kind of those collections. And then we've got stats specific for that item. But in here, you can also go through and look at, just for example, if you're curious about the pressure of that lump, then you come into that column and review that information. So again, these different names will be familiar for those of you working in Cinefluent, at least on the fluid side. The other thing is, since we did have part of that selection covered a combination of both nodes and lumps, you can come in here and you can see where we made that specification. So this is the collection that we studied, and these are the stats for that collection. Again, this is a little bit trimmed down. Like the only commonality between nodes and lumps is going to be their temperature. So that's really the only thing you can output there, and the temperature statistics mostly all make sense, but like you can't do really easily a capacity weighted calculation for that, at least without making some assumptions there. So that's not included, but everything else here is pretty much the same type of output. Okay, let's look into heat flow data. And one thing I forgot to mention too on the save file data is it does include a breakdown of the different runtimes. So if you're interested in only looking at, for example, thermal data and your fluid data call time was taking a long time and you don't need that information, then you can, there's options in the function to only call and get thermal data. So you can remove all of the processing and comp time associated with the fluid side there if you wanted to do that. Similar idea for registers. You don't have to pull all the nodes and lumps. You can only pull registers if you're interested in doing that. And there's even an option for that in the GUI. I didn't specifically call it out, but if you click this button, then it'll only pull the registers, which will be quite a bit faster than pulling all the info from the model. So in the heat flow data function, which I'll pull up again, this one is a bit different. Quite a few commonalities, runtime still here, inputs, units, etc. But the raw data is going to look significantly different. I will say, to get all the different interactions and different permutations of interactions, really, it can be relatively computationally expensive, and this list can grow very large if you have a lot of interacting submodels, like radiatively, for example. But this is just going to be a collection set of all of the different from and to references here. And one thing I'm going to do just to make it kind of easier to walk through really some of these outputs is I'm going to process this data again, but not using a collection of nodes and lumps. We're just going to do the default of fluid and thermal submodels, which by clearing the custom references will be what happens here. Okay, so coming back into the raw data here, now you'll see that there are a lot of interactions, that are possible here. So if we were to look at the save file data, we've got 54 different thermal submodels and 2 different fluid submodels. So depending on the different contactors, conductors, if you have radiative coupling between them, and that kind of thing, there can potentially be a large number of outputs that you end up seeing, a lot of different connections. So let's go ahead and in this, look at the raw data, first. Pull up this from, to, and a data set that corresponds. Okay. So in this first index, what we're looking at is the combination that involves the heat flow from the bar submodel to submodel 1, which will be at our first index. So inside of here, we'll see a breakdown of, at a particular time, the total amount of heat transfer, the linear rate, whether that be conductive or convective. In this case, it's 2 thermal submodels, so conductive. The radiative rate, the tie rate, if this was a fluid submodel interaction, the total number of different nodes that are kind of forming that connection, or the number of items, depending on if you have lumps making that connection. It'll give you kind of a breakdown of the quantity of different elements that are contributing to that interaction. So that's what you'll see here. But again, there's a lot of different permutations possible depending on how interconnected your model is. Which is also why the get heat flow data comp time is relatively quite a bit more expensive than get save file data, just because there's a lot more that has to be done. Inside the post-process data, let's check that out. So for one, throw up times here. So you'll see, again, there's a one-to-one correspondence here. We've got times, we've got 12 rows here, and so this first index in the data column would be at the end, it looks like, of the steady state solution that this run included. But if, for example, for whatever reason, you're interested in seeing what the data looks like at timestamp 8, that would be index 10 in this case, we'd come into this data set. So I'm just going to throw this up so we can look at this in more detail. And again, this time will be ported over. You don't have to guess so much well, it's not guessing, but you can look at those indexes and figure it out, or you can just ping into here if you're wanting to do that too. So it'll include the time and the record number and the particular combination that you're looking at. So from bar to submodel 1, it includes the temperature of that from submodel, and this will be the capacity weighted average if capacitances were output to the save file. If not, it'll just be the average. And if it's a fluid submodel, it's just going to be the average, which in this case it's not. Just calling that out. The 2 temperature, so you can see that we've got from temperature is a little bit higher than this 2 temperature, and we have a total heat transfer rate of 110 watts here. Well, technically it's just 110. You'd have to look at the save file units to actually see the units on this. So it's just a big breakdown of all of the different combinations that are possible, and the associated rates for each one of those different kind of permutations. Okay, that's pretty much it. There's a bunch of different examples here. If you want to do things programmatically, if you want to generate your own network diagram, which was that kind of energy flow between different submodels, there's directions on how to do that without having to use a GUI. There's some other breakdowns on if you wanted to output data to a spreadsheet. There's information on that. There's also information on doing your own time weighting. So like, I think that's located up here. One sec. yeah, the time weighted section is in here, so you can look at some different options there. Definitely recommend reading over this example script, looking at the different programmatic calls you can make. I will say that I've batch processed, hundreds of different save files using these utilities to go and look at parametric results or that kind of thing. And I tried to emphasize comp time and the construction of all these different functions. So, I mean, I've been able to process thousands of save files across hundreds of timestamps, within 10 minutes or so, depending on how often you're outputting that information, but really pretty quick. So definitely recommend it. Hope you guys get some use out of it, and I appreciate any feedback. So please let me know if you've got any feature requests, additions, or issues. Just kind of let me know what your thoughts are on it. I would appreciate it. Thank you.